Hi everybody, welcome back to the lecture Video Coding, this time about more compression approaches. So what are more methods to use redundancy to compress our image or video? So in addition to the DCT which we just saw. For redundancy reduction we need a source model. A common source model for natural images is that they have many even surfaces, meaning that there is a high correlation between neighboring pixels. So meaning neighboring pixels have quite similar brightness and color. So a simple method to use this correlation between neighboring pixels is predictive coding. One example is the so-called DPCM, or differential pulse code modulation. So here you can see the principle. So imagine we scan our image line by line, row by row, and then we are at this point. And at this point we want to predict the pixel which comes next. So this is something that can be done in the encoder and the decoder. And when we are good at predicting this pixel, then we can either not transmit anything at all or just transmit the difference between the actual and the predicted value. So at this point we have already a neighborhood to this pixel. So we have the pixels A, B and C. So taking our assumption of more or less even surfaces, then we can assume that A, B and C must be quite similar in value, brightness or color. So here we would like to predict the current pixel as accurate as possible. We then transmit only the difference of the actual pixel value to the predicted pixel value. If the prediction is accurate and the signal is predictable, we will get many small prediction error values. Since we have a high probability for those small values, we assign short code words to them and leave the long code words to the less probable higher values. This is the principle of entropy coding. So in this way we obtain a reduced bitrate. An example for a very simple prediction would be to use the pixel just before to the left, which would be A, as predicted value. So we would assume that this value just repeats. A slightly more complex method would be to compute the weighted average of the values of the pixels A, B and C in the neighborhood that we just saw for the predicted value, assuming they are not identical anyway. We don't need to limit ourselves to pixels A, B and C. We also can take a larger neighborhood into account. So this would be useful, for instance, if we have a shadow which increases or decreases in a certain direction. Then we have a more or less linear increase or decrease of brightness, which we could then also easily predict. So we could predict how fast the brightness is changing and in which direction. So this usually gives us a modest compression with low complexity. So this is also described in the book by Richardson, Video Codec Design. And this is also called intra-frame prediction. Right? Intra meaning within this frame, as opposed to inter, which means between frames. Yeah, and this inter between frames is now what motion estimation is doing. Right? So this is the next approach. So we can extend this approach from two-dimensional images to our three-dimensional video sequences, where we now also have time as the additional dimension. So this would be inter prediction. We not only have neighboring pixels in the spatial domain, x and y, but also in the temporal domain, pixels in the previous and also following frames. Right? You would ask, how can we actually take pixels from the following frames? Well, we just have to delay playback, right, in the decoder. So we just wait until the following frame arrives, and then we encode them together. And also in the decoder we would do the same thing, which would mean that the decoder can only play back after a certain delay, so that the previous frame is reconstructed from the following, which would be the current. Yeah, so in this way we simply extend our neighborhood of pixels and could again apply a weighted sum to obtain our prediction, right? Weighted sum between pixels in the same frame and neighboring frames. So this would also work reasonably well, but we can improve our temporal prediction by the model assumption that we have a constant, which means not changing objects in our video sequence which move smoothly, right? So here it's not like shadows or light that changes slowly, but we have objects which are moving, and those objects usually they are fixed, well, at least if they move parallel to our image plane. And this is what we assume here. We have an object, and this object does not change in itself, but just moves to different places in our frames. Yeah, so to use this model assumption, we search the picture for displacements, so-called displacements, which are movements, and estimate motion vectors for the image, right? So that's an important point. If we have two frames and we have a moving object, then this object appears at one position in the first frame, and then it appears in the shifted position in the next frame. And you can compute x and y values for this shift. And those x and y values, these are two values, and those two values form a vector, right? This would be the motion vector. So these motion vectors then increase the accuracy of the prediction over the time dimension. Again, assuming our assumption to be true, because then we can simply apply a motion vector to our object or part of our object, and instead of repeating our object again, we just take all those pixels and shift them to the new position for our prediction. Yeah, so the prediction error is then computed based on the motion compensated predicted image. So first we compute the prediction, and then we compute the difference between the predicted and the actual picture, and this is then transmitted. And the decoder does the same thing. The decoder also uses the motion vectors. Those motion vectors are usually transmitted as side information to the decoder, so the decoder does not need to compute them. It gets them from the encoder, so it can do the same prediction using the same motion vectors, and then simply adds the difference to it. So the difference again is the prediction error. So the encoder computes the prediction error, transmits it to the decoder together with motion vectors, and the decoder computes from the motion vectors the predicted image and adds the prediction error to it to get the actual image. Yeah, the decoder can compute the new frame using the motion vectors, the previous frames to which it applies the motion vectors, right? So that also means that the decoder, as the encoder, needs to have a memory of previous frames to be able to make this prediction, the motion compensation prediction. And perhaps also future frames, if you also compute motion vectors based on future frames. So we need to have this frame memory which contains all those frames on which our motion prediction is built upon. Yeah, so the decoder takes this prediction plus the residual frame to compute the current frame. The following image shows this basic approach, right? So here you can see it. Here's the encoder, and here's the decoder. So this is the dividing line between the two. So here you can see we have the current frame coming from the camera, and taking this current frame, we subtract the prediction. And this prediction is based on motion estimation, and those motion vectors which are used in this motion estimation are computed from comparing the current frame here to previous frames which are in the memory. So this is the memory of previous frames. So then the motion estimation computes the motion vectors, and then using the motion vectors we create the motion prediction. So this is then subtracted here and we get a difference image, the difference between the motion predicted and the current frame. And here you can see there's also a line going from the motion estimation to the decoder. This is the side information containing the motion vectors. Right here you get all the motion vectors transmitted to the decoder, such that the decoder can create the same prediction as the encoder. So here you can see create prediction is on both sides, right? And also on both sides we have previous frame, the previous frame memory, right? So that's also important that both have the same memory, otherwise they would compute different predictions, which we don't want. Right, so we need to make sure that the previous frames are the same. So here the previous frames are the previous reconstructed or decoded frames which are going in here. And that's the same here in the encoder. Here you can see we have an image encoder, and here we have an image decoder. This is basically the same as we have here in this decoder, right? Or rather, taking this one here. So here we have the decoder in the encoder. So this is done such that the frame memory has the same frames as the decoder, including all the quantization errors that are going on. So here we need to have quantization in this encoder, and here we have dequantization, and this introduces quantization errors. So the decoded frames, they contain quantization errors. So what's in this memory here is previous frames including quantization errors. And that's why it's important to also have the same previous frames here in the encoder, the same previous frames including the quantization errors. And that means also this difference is computed including the quantization errors. So here this difference then partially compensates for past quantization errors, and in this way we make sure that both encoder and decoder run in synchrony and have the same previous frames. Yeah, again, this is this picture is from the book Richardson, Video Coding, Codec Design. Yeah, so here are a few important terms. Motion vector is the vector which describes the motion of an image block, because usually we compute vectors, the motion vectors, for each 8x8 pixel block in an image. It doesn't have to. Later we will see that there's variations on it, but for now assume we compute those vectors for each 8x8 block. Then motion prediction is the algorithm which computes the predicted image. Motion compensation is computing the prediction error using motion prediction. And motion estimation is the estimation algorithm for estimating the motion vector. Yeah, so this is basically what I just mentioned. Observe the image decoder in the video encoder. It is necessary because only in this way the video decoder has the same basis for its prediction as the encoder. If the encoder would take its original frames as basis, which it could, its prediction would be different, and this would lead to the so-called drift between encoder and decoder, with increasing degradation of quality over time after decoding. And this is because the decoder would have different past frames than the encoder, and hence the difference would not fit anymore. This is especially important for long prediction sequences. For short prediction sequence, like if every second frame is a so-called intra predicted frame, intra means no motion prediction, which is not predicted from past frames, this might be less of a problem because the drift needs some time to accumulate. Yeah, so how do we compute those motion vectors? We can look for motion of individual pixels if we take into account a neighborhood of pixels which then overlap, or blocks of pixels, for instance our 8x8 blocks, which then don't overlap, or complete objects in the frame. What is most often used is a block-based motion estimation. Usually our 8x8 blocks are also 16x16 blocks. And larger blocks here are useful because we need to transmit all the motion vectors to the decoder, and the more of those we have, the more side information bitrate we get. So going to larger block helps compression because we have less side information. So that's why this is attractive. Yeah, so this means for each of these consecutive non-overlapping blocks in the current frame, we compute a motion vector to see from which position the block came from in the previous frame, which can be seen here in this picture. So here we have the current frame, and for each block of the current frame we search where it came from in the past frame, right? And these are then the resulting motion vectors indicated as those arrows here. Here observe that the motion vectors have a length and a direction. Different standards use different precision for the motion vectors. For instance, pixel accuracy, which means it's accurate to 1 pixel, or subpixel accuracy, could be half pixel or quarter pixel. And it actually makes a big difference in compression performance. You can imagine the more precise the motion vector, the smaller the difference, or the more precise the prediction will be. Yeah, so how do we obtain those vectors with different accuracies? So first we take a block of the current image and shift it pixel-wise or subpixel-wise over a certain neighborhood of the previous frame and look for the biggest similarity or correlation between this shifted current block and the block in the position of the previous frame. Observe that usually we only have plane motion in our model, not rotation or stretching or shrinking. This is a restriction, but it also simplifies our task of finding suitable motion vectors. This means we also need a similarity measure. What is usually used is the mean squared error between the predicted, the shifted previous, and the current block. So here you can see it. This is how we define our mean squared error. So this is simply the double sum over two candidate blocks. So C is the current block and R is the reference block at the shifted region in the previous frame. Right. So here reference would be some shifted region of the previous frame, which we call reference block. And then we need to compute how similar they are. So we simply take the difference of all the pixels, square them, and take the average. Yeah, capital N is the block size. Alternatively, instead of taking the square, we can simply take the magnitude. This is called the mean absolute error, MAE. So in each case, the square and the magnitude is to make sure that the difference, that we have positive values or non-negative values that we compute the average over. Yeah, and non-negative is important so that they don't cancel out. Okay, so that should be it for now. Thank you for your attention and see you next time.